Hi, Assalamualaikum everyone. In this video, we are going to continue our Smith chart tutorial with L network impedance matching using Smith chart. So for that purpose, we're going to use the ZY chart to do the impedance matching. So a bit about this ZY Smith chart. It is a combination of the Z Smith chart on the right here and the Y Smith chart on the left here. Okay, the Z Smith chart, which represent the impedance, is represented in red circles and red arcs, while the Y Smith chart is represented by the blue circles and arc lines. Okay, and if you notice at the center here, this is the point where Z equals to 1 and Y also equals to 1. So that will be our Z naught point. Okay, and each circle on the Y chart is representing the conductance, while each arc represents the susceptance. Okay, and actually the Y chart is the flipped and rotated version of the Z chart. So to further understand the ZY chart, let's do this simple example. Okay, this is the same example that we use in video tutorial, Smith chart tutorial video 1. Okay, where we want to plot load impedance of 100 plus J 50 ohm, and the line impedance is given as 50 ohm. So the normalized load impedance is given as 2 plus J. Now we can easily plot this point on the Z Smith chart like so. Okay, we find the corresponding Z or R, and we find the corresponding X for this load impedance. Okay, now if you notice here, we can also represent that same point by using this blue circle and blue arc, which is the Y Z chart. Okay, so let's have it. Let's look at that. So the same method also apply. We trace we trace the circle of that point, which is this one, and then the arc, which is here. Okay, so if we read the Y chart, so the Y for that point is 0.4 minus J 0.2. Now notice that for the Y chart, for the imaginary value, if the point is on the above of the line here, if it's for example located here, the imaginary value will be negative. But if the point is somewhere on below the line, below the middle line here, so the imaginary value will be positive J. Okay, this is because the Y Smith chart is the rotated and flipped and rotated version of the Z Smith chart. Okay, Smith chart can be used to design the L matching network, which can consist of either one or more series inductors, series capacitors, shunt inductors, and shunt capacitors. Shunt here meaning parallel. Okay, and the configuration of the L network depends on the location of our load impedance, normalized load impedance on the Smith chart. And to design the L network, what we do is we move on the Smith chart circles and arcs, okay, until we reach the point Z naught, or the point where Z is 1 and Y is 1 on the Smith chart. Okay, and the movement that we do represents the inductors and capacitors on our matching circuit. Okay, here are some examples of the types of L network for impedance match, where it depends on where our ZL is located on the Smith chart. For example, let's say, let's look at the first one. If our ZL is anywhere in this region, let's say if it's here, so that to match do impedance matching for this load, we can use this configuration or this circuit. However, this is not the only solution. Okay, we can also, if the point is here, we can also use this configuration to solve our problem. Okay, so it doesn't necessarily have to be one solution for one impedance load. Impedance network matching. Okay, it can be more than one solution. Even we can even solve it by only using, for example, here by, let's say if the point is here, we can solve it by only using the capacitor, or in here we can, if the point is somewhere in here in this region, we can solve it by using only inductors. Okay. Okay, earlier I mentioned that movement on the Smith chart represents the elements that we're going to add into our L network impedance matching circuit. So let's look further into what these movements on Smith chart represent. Let's say if we look at our Z Smith chart over here, if our target is moving towards the Z naught at the center there. Okay, let's say if we move on a clockwise movement on the Z Smith chart. So what that means is that we are adding serial inductance to our L network, and to find the inductance we're going to use this equation. However, if we are moving in a counterclockwise movement, so what happens is that we're going to add a serial capacitance into our impedance matching circuit. Okay, and this is the equation that we're going to use to find C. If we're moving in a clockwise movement along the Y Smith chart, so what we're adding is a parallel or shunt capacitance, and this is the equation to find it. If on the other hand we're moving in a counterclockwise movement, we are adding a shunt or parallel inductance, and this is the equation that we're going to use to represent to find the inductance. Now let's look at an example. Let's say we have a circuit like this where there is a RC load with a load impedance of 200 minus J 100 ohm, which is connected to a 100 ohm line, and we want to match this ZL to our Z0 here. Okay, so for that purpose, the first step is of course to plot ZL on the Smith chart. Alright, and as usual, we find the normalized ZL, which in this case is equal to 2 minus J1. Okay, and we plot ZL on the impedance chart, and the second step, we find the shortest way to go from ZL to Z0 and then calculate the movement. And the final step, we calculate the C and L using the formula earlier. Okay, for this purpose, if you refer to the previous slide, the two possible solutions are available. Either we use the circuit on the left here, or the circuit on the right here. Okay, so let's move on to the next slide. Okay, the first step is to plot the ZL. ZL normalized, which is equal to 2 minus J1 on the impedance Z chart, which is on the right here. Okay, so if you plot that, So it is here, located here, and let's write that down. Okay, so that is our load impedance on the Smith chart, normalized load impedance. Now the next step is to get the admittance or the YL normalized for that point. To do that, we read off the Y Smith chart. Okay, like that. And let's just name that, or rather we put that as YL prime, which is, if we read the Y Smith chart, equals to 0.4 plus J 0.2. So please be careful with the imaginary value of both the Smith chart. Okay, now the next step is to move along the reactance G 0.4 circle until you find the Z equals to 1 circle, or the other name for it is the unity circle. Okay, and let's call this movement 1 and that point as A. So what does it mean? So we're going to move along this 0.4 G equals to 0.4 line until we find a point where it meets this red circle here, this Z equals to 1 circle. Okay, when we found that point, we just label it as any label you want. Let's say we label it as A, and we read off the Y Smith chart and get the load impedance, the Y of that point. We call it YA prime. Okay, which is equal to 0.4 plus J 0.5, which is down here. Okay. Now the next step is to move from point A to point Z equals to 1. Okay, and this, how do we do this? We move along the Z equals to 1 or the unity circle. We go along here until we find the center point here, which is the Z naught. Okay, and let's call that as movement 2. Okay, so we now have moved from our original point here. We have moved here, and then we have moved to the center of our Smith chart. Okay, so now the next step is to calculate or to interpret what this movement represents. Alright, now the third step is to calculate the movements. So, as I mentioned earlier, that the movement represent what element do we put on our circuit. Okay, so let's look at the first movement here. So this movement is the represent the element closest to our load here. Okay, so in this case, we are moving counterclockwise on the Y Smith chart circle. Okay, so what it represents is a shunt capacitance. Okay, or shunt capacitor. And then the next movement, M2, is where we move in a clockwise movement along the the Z Smith chart circles. Okay, there are circle for the Z Smith chart. So what that represent is the serial inductance. Okay, so our circuit is going to consist of a serial inductance and a shunt capacitance. Okay, and here are the two formula that we're going to use to calculate them. Alright, now let's look at how we can calculate this L and C. So let's focus on the movement 1 first. Okay, the starting point of our movement is we move from ZL prime here. Okay, and then we move to point A. Okay, ZL is a 2 minus J1, or in Y equals to 0.4 plus 0.2, and our point A, the Y for that point A is 0.4 plus J 0.5. So to find the value of the capacitance, first we must find the movement from start to end point, which is we call it BC, okay, and it is equals to YA minus YL, alright, which is 0.4 plus J 0.5 minus 0.4 plus J 0.5, which we get equals to J 0.3. So that is actually the value of our capacitance if we directly read it off from this Smith chart. Now the next step is of course to find the capacitance, and the capacitance can be found by using this equation as shown earlier, and it is equal to 0.92 picofarad. Okay, this B here is we take the imaginary value of our B earlier. Okay, so it's just a matter of replacing that B inside the equation so that we get the value of our capacitance. Okay. Alright, now let's move on to movement 2. Okay, in movement 2, point A is the starting point and Z0 is the end point. So we are moving from this point here up to this the center here. Okay, and now for movement 2, previously in movement 1, we are going on the blue circle, which is the admittance circle, the Y Smith chart. So therefore we are when we find the movement, we are calculating it with using admittance or Y. Now for movement 2, we are moving in the, if you notice here, on the red circle here, which is the Z Smith chart. So now instead of calculating the movement by using the admittance Y, now we are using the impedance. We are using Z. Okay, for that purpose, we need to find the impedance for point A, which can be easily found by looking at the arcs of the circle and the arcs of that point. Okay, so the ZA prime for point A is 1 minus J 1.2, which is our start point, and our end point is Z not in the center here. Okay, now the next step is to find the value of inductance. First, we must find the movement from start to end point, similar to the movement 1. So but in this case we are calculating the in terms of impedance. Okay, so we represent that movement as XL. So XL is endpoint minus impedance of endpoint minus impedance of start point. In this case endpoint is 1, so 1 minus 1 minus 1 minus J 1.2. So in the end we got it XL as equals to J 1.2. Okay, and finally the last step is to calculate the inductance, similar with our previous calculation within capacitance. What we need to do is just replace this 1.2 inside the formula earlier. Okay, so L equals to X Z0 divided by 2 pi F. So we replace X with 1.2. In the end, we get L as 38.8 nano Henry. Okay, so that is our inductance for our matching circuit. So now we have completed our calculation, and as I mentioned earlier, this is not the only solution. So the one we did in this example is this one, solution 1. There is another way of solving this problem, which is by, instead of moving down to find the unity circle, we can also move upwards. Okay, we move upwards and we find the unity circle. So if we do that, what we're doing is we are adding parallel or shunt L to our circuit. And the next movement, this is movement 1 for solution 2, and the next movement we move downwards and find our Z0 in the middle here. And what we do, if we move downward like this, we are adding serial capacitance to our serial capacitor to our matching circuit. Okay, and this is how our both of the solution looks like. This one is the one that we did earlier, so this is the circuit for our the solution that we did earlier, and this is the solution number 2. If the first movement is moving upward instead of downward. Okay, for this one we are moving downward, the first movement, and for the second solution we are moving upward. Okay, and it looks like there is a bit of difference between the two, actually a lot of difference if you look at the value here. And this value has been run and we found the reflection coefficient. It seems that solution 2 seems to be a better match at higher frequency for this circuit. Okay, so it goes to show that there can be more than one solution to impedance matching technique for one problem. Okay, so you can use either one solution as long as you follow the rules of the movement of along the Smith chart. Okay, so that's it for this video. I hope this video will help you to solve problems involving impedance matching. Okay, thank you for watching. Bye.